Hello, this is the brief review of the reading for Chapter 6. We will talk about related samples T, effect size, and confidence intervals. In this video, we'll apply the 4 pillars of scientific reasoning to a research example comparing 2 sample means that were collected from the same group of people. In other words, we'll be applying them to a situation where you would use a repeated samples t-test. Now you're going to use the related samples T when you're trying to compare 2 sample means to each other. And this can happen in 2 different situations. Perhaps the most common situation would be like a pre-post design. You measure somebody's, say, cholesterol, then you give them a cholesterol drug, and then you measure their cholesterol again, maybe a month later after the drug has had time to have its effect. So again, you're measuring the same people in 2 different conditions. Another situation where you might use this type of design is something called a matched design, where you have pairs of participants and one person is in each condition. So to use the cholesterol example again, you might have someone who has 200 cholesterol level right now. You might find somebody else who also has a 200 level cholesterol, and you would assign one of them to get the cholesterol drug and one of them to get a placebo drug. But you're pairing them because they're matched on some important variable. In this case, it would be cholesterol, but it could be anything, right? And then you're pretending like these paired people are really the same person. In either of these situations, you would be using a related samples t-test. Now, the related samples t-test is very similar to the single sample t-test and another t-test that we'll talk about in the next chapter. All t-tests use a similar logic. They have the obtained difference or the observed difference between either a 2 sample means or a sample mean and a population mean or a sample mean and a value of interest. Just an observed difference between what the data said and what you expect if the null is true. And you divide that by expected sampling error. Now, the way you compute sampling error is a little different for every t-test, but the logic, again, is the same. You're just comparing the amount of variability you have to the amount of variability you expect due to sampling error. And if you get a t-value that is substantially different from 0, then you will get a small p-value, which will be strong evidence against the null hypothesis. Now, the research question we're going to use in this example is, does voice-to-text technology, you speak into your cell phone, for example, and then it will automatically type out the text for you. Does that type of technology result in fewer off-road glances than manual texting if you were texting while driving? Now, this is not an endorsement for that. It's a bad idea. You shouldn't do it. The fact is, people still do it. So researchers look at ways to reduce the danger. One study found that it did reduce the number of off-road glances. So they argued that it made it safer, not safe, but still safer. And they found a very large effect, an effect of 1.33. So if you go back to chapter 5, it will tell you that if you're trying to find a large effect, if the research suggests a large effect is what's going to happen in this design, you can use a sample size something like 25. That would be like statistical power, because a researcher in literature suggests that the effect is going to be large, and so statistical power is the appropriate metric to use, and that table will tell you that you can get by with 25. Now, the procedure involves using these 25 people in a high fidelity driving simulator for 7 minutes. They're driving through different scenes, and periodically they would get a text that they would need to read and then respond to. They all got to use their own cell phones, and they got to practice using the voice-to-text technology if they weren't familiar with it. And then after they were able to pass some proficiency tests, they went ahead and did this procedure. They randomly assigned half of the participants to do the voice-to-text technology first, and the other half did the manual texting first. And that's a good methodological control to battle fatigue and things like that. And the study that we're going to be analyzing the data for did the same thing as that. So it had good, solid procedural controls. The first step, of course, is hypothesis testing with a continuous p-value. And the first part of that pillar is choosing the correct test statistic. And as we've indicated, in this situation, you're going to want to use a related samples t because you're comparing two sample means that are collected from the same group of people. In this scenario, we've got, again, people driving a simulator, but they're going to be driving the simulator twice, right? They're going to be driving it once using the voice and using the voice-to-text technology to reply to texts, and in the other condition, they're going to be using a standard keyboard manual texting method to respond. And so again, the same people are in both conditions, and so that makes it a related samples t-test. The next step is to assess the statistical assumptions. This test has 3 statistical assumptions: data independence, which is the same as data independence was for the single sample t. Any individual participant's responses should not influence another person's response. So it's just good positive control. You don't want to have one person influencing another one. In this case, the appropriate IV and DV measurement is that the IV is going to define 2 different conditions. In this case, the IV is the type of texting methodology they're using, either voice-to-text technology or to manual texting. So that's the independent variable with 2 levels. The dependent variable for this type of test is going to be measured on an interval or ratio scale of measurement. And then finally, the normality assumption is that the distribution of sample means is going to have a normal shape. It's actually the distribution of the sample mean differences. We'll talk about that in a second. But it's going to have a normal shape. And of course, because you know the central limit theorem, you know that if the population has a normal shape, then the distribution of sample means will as well. Also, you can get a normal distribution of sample means if the sample size that you're using is sufficiently large. Usually we use a thing around 30. We can expect the population to have a normal shape in this situation, so we're not too worried about the normality assumption. Next, we want to identify the statistical null hypothesis. And again, as always, the statistical null hypothesis is what you'd expect if there is no effect. In other words, in this case, if there is no difference in the number of off-road glances produced when using either of the 2 texting methodologies. If that is the case, then you would expect that mean difference to be 0. You would also, if you were to get a mean difference of exactly 0, that would give you a t-test of 0 because the numerator of the t-test would be 0. So the t would end up being 0 if you get a mean difference. And then again, if the null hypothesis is true, any deviation from a t-test of 0 would be due to sampling error. I'm going to get the pointer out for you here. Okay, so again, if the null hypothesis is true, you expect to get a mean difference of something close to 0. Then you're going to plug that into the t-test formula that we'll show you in a bit. And once you plug, if you were to get a mean difference of 0, then that would give you a t-value of 0. So again, this is the distribution of sample means for the mean differences. And if the null is true, you expect to get a mean difference of 0, which would give you a t-score of 0. So if the null is true, a t-score of 0 is very common. A t-score in the faraway tails is very uncommon. So if you get something far away from a t of 0, that would be compelling evidence against the null hypothesis. The next step is to graph each condition. So looking at the graph, you can get a general idea of the results you're going to get. Again, the dependent variable is the number of off-road glances that occurs while texting and driving. In the keyboard manual texting condition, it was about 3. And then this is a 95% confidence interval around 3. And in the voice-to-text technology, it was somewhere between 2 and 2.5. So a difference of, maybe 0.7, 0.8. Less off-road glances. So here a lower score would be better. So you know that you still need to go, of course, do the t-test to decide if the p-value is compelling enough to say that one texting methodology works better than the other in terms of having fewer off-road glances. But at this point, you know that if there is a difference, the keyboard texting condition had more of them. So this tells you clearly which direction the effect is going in. And now we want to compute the actual t-test. Again, as I said before, this is the mean difference. You can get this mean difference by simply taking the mean before and the mean after and finding the difference between those two means. I shouldn't say the mean before and the mean after. I should say the mean for the voice-to-text technology and the mean for the manual texting technology, and find their mean difference. And it was about 0.8. And then you divide by sampling error, and this sampling error is the standard deviation of the difference scores. So you take each person's difference score, how far each person's score is different for their own voice-to-text condition and their manual texting condition, find each person's difference in performance, and then find the standard deviation of all of those difference scores, and then divide by the square root of n, the sample size, and then you would find that in this case, the obtained t-value is 7.62. Now, here is a normal curve, a distribution of sample means, a t distribution, if you will, and the obtained t-value is way out here. I mean, it's very far into the tail. So this is going to be very compelling evidence against the null hypothesis. Again, if the null is true, we expect to get something close to 0. And is it possible that we could get something out here and have the null still be true? Yeah, it's possible, but it's very, very unlikely. Now we're going to be doing a two-tailed test here because that's the appropriate test, because either tail would have a result on either direction would have important implications for the population. So it's appropriate to do a two-tailed test. If you, again, if you do this on a computer, the computer will give you the p-value. And in this case, the p-value is very small, 0.001. That means that the probability of getting something this far away, a t-value this far away from 0, on the positive side of 7.62, or on the negative side of negative 7.62, something outside of that range of plus or minus 7.62 on the outside to the tails is very unlikely. It's going to happen less than 1 time out of 1,000 if the null is true and there's no methodological flaws. So this is very compelling evidence against the null hypothesis. Now we do need to interpret the p-value. I jumped ahead a little bit on that previous slide, but I would like to spell it out again. Again, it's a two-tailed p-value of 0.001, less than 0.001. That tells you that the probability of getting that t, or something further from 0, if the null is true and there's no methodological flaws, is very small. Therefore, this is compelling evidence against the null hypothesis. There does seem to be a difference. And because we remember looking at the graph, you know that the voice-to-text technology had fewer off-road glances and the manual texting had more. These data are compelling evidence that the population of drivers, if they were to use one technology or the other, would lead to a different number of off-road glances. Specifically, manual texting leads to more off-road glances than does voice-to-text technology. The next step is the second pillar of practical importance with an effect size. And again, you have two options. You can use a mean difference, or you can use a standardized effect size. The mean difference was, again, about 0.8, and that simply means that the voice-to-text technology had about 0.8 fewer off-road glances in the procedure. And again, the procedure was about 7 minutes long. And would this have practical importance? Well, probably. If someone's taking say an hour-long drive and every 7 minutes they have 0.8 fewer off-road glances, that's quite a few more off-road glances. And that means that there'd be that much less possibility of them having an accident, because accidents tend to occur when something happens when they're not looking at the road, when they're attending to the text rather than the road. Something unexpected happens. So the more time people's eyes are actually on the road, the safer it is. So if, again, longer ride with a lot of texting going on is going to have more danger if people are using manual texting versus voice-to-text technology. But sometimes a mean difference is a little hard to interpret. This one isn't too bad, but there are other options, and that is the standardized effect size. Now, with a related samples t-test, there's actually two ways of computing what is a standardized effect size. One is more standard. It's taking the mean difference divided by the standard deviation of the differences, and that's going to tend to give you a larger effect all the time. In this case, it's huge. These will tend to give you very large effects. So again, a 0.8 is considered large. This is nearly double that, so this is an extremely large effect. Another way to do it that is less common, but probably is a little more accurate, a little more less inflated, is taking the mean difference and dividing that by the average of the standard deviation of both conditions. In that case, this would come out to be a 0.5, which is about a medium effect. Now, this is a less commonly used one, but again, I think it's probably a more appropriate one. Unfortunately, a lot of the computer programs, including JASP and Jamovi, they will compute this type of D, the D sub Z. It will compute that automatically, but it will not compute this automatically. So if you want this one, you will have to do it by hand. But again, luckily, it's not hard to do. One thing to remember when you do this, again, is using a standardized effect size is generally going to be the way to go if you want to compare your results to another study. Again, it's standardized so that as long as they standardize their results too, they're kind of putting it on the same scale. Although it is important to tell which of these standardized effect sizes they're using. Obviously, they give very different results. It's not that one is right or wrong necessarily, but as long as you report which one you did so that people know, Are you using one that tends to give a higher value, or are you using one that tends to give a lower value? Just report what you use and you'll be fine. The next thing you want to do is pillar 3, which is the population estimation with confidence intervals. And as with the previous 2 chapters, you find the upper bound and lower bound by finding a point estimate and then adding a margin of error to it and subtracting a margin of error to it to get the upper bound and lower bound respectively. So in this case, the point estimate is the mean difference between the 2 conditions, which was again 0.792. Then you're going to add to that the margin of error and subtract the margin of error. Again, the text will go over how to compute the actual margin of error. I'm going to skip that step here because mostly we're going to be focusing on interpreting these things, and you'll be using computers to generate these values. In this case, the upper bound was about 1 and the lower bound was about 0.6. So this is suggesting that the difference in the number of off-road glances in the population, if they were to use these 2 different technologies, would be as high as 1 off-road glance every 7 minutes to as low as 0.6 or so every 7 minutes. So again, in a long drive, this might lead to quite a few fewer off-road glances if you're using the voice-to-text technology, which is associated with fewer accidents. You can also compute a 95% confidence interval around D. Again, you would use a point estimate and add a margin of error, but this is typically not done by hand. You use computers to do this. But in this case, the upper bound, and again, this is around D sub Z, so this is going to only be around the bigger D value. This is suggesting that the effect size is very large, and even the smallest plausible effect size of 0.948, that's even a large effect. So now you got to keep in mind this is the type of D that does sort of tend to inflate the effect a little bit, but still this is pretty compelling evidence that the effect has that the difference in technology is fairly large in the population, and you could expect if everyone were to transition to this other technology, that it would result in a pretty substantial reduction in off-road glances while texting and driving. Again, texting and driving is still not a good idea, but the voice-to-text technology does reduce the risk considerably. And as always, when you get done, you need to consider about how strong the research methodology was. This study has some really good characteristics to its methodology. It used a high fidelity driving simulator. It let people use their own phones so that they weren't unfamiliar with the phone when they were doing it. They got to practice ahead of time if they weren't familiar with the voice-to-text technology on their phone. They had to pass a proficiency test to make sure that they knew how to text well, both manually and with the voice technology. So they were well practiced. And they also used counterbalancing. They had half of the people do each condition first, and the second one second, of course. That means that maybe people weren't fatigued by the second one. If everybody did the voice-to-text technology at the second time, maybe they were fatigued when that was going on, or whatever. So they counterbalanced, so that would balance out. Again, counterbalancing means that half of the participants did each condition first. You also should consider the scientific literature. How do these results compare to those reported by others? Well, we started by thinking about a study that was done by other researchers, and they found very similar results that we found, that voice-to-text technology did reduce the number of off-road glances. We found very similar things. You should also, so you want to compare your results to theirs, and in this case, they're very similar. You also want to provide your interpretation of the results if it's appropriate to do so. In this case, I think it's very appropriate because Just because voice-to-text technology is safer than manual texting, that doesn't mean it's safe. So it's important when you have sort of a nuanced result that you lay that out. You're the expert. You just conducted this research. Somebody else is going to be interested in your opinion, in your interpretation. So don't keep them waiting. Provide it. You know more about it than anybody else. It's your study. So don't be afraid to give your interpretation of the data. People are going to want it. Now you need to report your results. And as in the previous chapter, I've tried to color code this response here to highlight the different components of a complete answer. Your answer should have 6 components. You should say what type of test you did, what you were comparing, and how you compared it. You should put in the statistics in APA format. Interpret the p-value, the effect size, the confidence interval, and then comment on the methodology and compare your results to the literature to the extent that you're able. So in this case, we computed a repeated measures t-test comparing the mean number of off-road glances using voice-to-text technology to keyboard texting. And then you include all of the statistics. Here's the mean for the voice-to-text technology, the mean for the keyboard texting. You ran a t-test. It had 24 people in it, and this is the degrees of freedom, so it's 24 minus 1. Here's your obtained t. Your p is less than 0.01. 0.001. Tell them that it's a two-tailed test, and then report your D. Notice how I reported the D. I'm telling them which kind of D I used here with the subscript Z. Now we need to interpret those results. First, I want to interpret the p-value. Participants had fewer off-road glances when they were using the voice-to-text technology than keyboard texting, and this difference is unlikely due to sampling error. That's because this p-value was so small, right? This data is very compelling, suggesting that the voice-to-text technology reduces off-road glances exceeding 1.6 seconds. That's the definition of an off-road glance. If their eyes weren't off the road by more than 1.6 seconds, it didn't count. So they only counted long off-road glances. And that behavior of glances being more than 1.6 seconds off the road is associated with increased accident risk by certain researchers. So again, all of this is an interpretation of that p-value. Next, we want to interpret the effect size. The observed effect size for the population, if they used voice-to-text technology instead of keyboard texting, would be a meaningful reduction in dangerous off-road glances and consequently a meaningful reduction in accident risk. For example, for an hour-long drive with 36 texting exchanges, voice-to-text technology would result in 6 to 7 fewer off-road glances. Fewer off-road glances likely means fewer accidents and fewer deaths. So all of that is, I did more than just say what the effect size was. I'm offering an interpretation for it. So sometimes you don't need an elaborate explanation, but sometimes you do because the effect size is somewhat nuanced, and for people to understand its effect, you need to explain it to them. Again, you're the expert. You know more about the study than anybody else. So if it has an important implication, it's really your obligation to make that implication clear. Next, you want to talk about the confidence interval. The smallest plausible effect for the population would still be a large reduction in off-road glances for those using voice-to-text technology. Now, in this case, the interpretation is focusing more on the lower bound of the confidence interval range, but I think that's okay here because the lower bound was still large enough to have practical importance, and that's just worth pointing out. It's not that every one of these different components you have to say as much about it. In some cases, I think some of the statistical evidence is more important than others, and it might not be the same in every scenario. In this situation, I think the effect size is a little more important, so I decided to spend more time talking about that. Finally, I want to talk about the methodology and literature. That's what I'm doing right here, and I'm offering an interpretation, as you'll see as well. It is important, however, not to misinterpret the meaning of these results. These results do not suggest that voice-to-text technology makes texting while driving safe. Rather, they suggest that voice-to-text technology makes driving safer than keyboard texting. But interacting with voice-to-text technology could produce substantial driver distraction of its own by increasing the cognitive workload drivers experience, by taking their mind off the road. In fact, Strayer's 2015 found that voice-to-text technology increased the cognitive workload of drivers threefold relative to driving alone. Consequently, using voice-to-text technology to text while driving increases risk relative to not texting while driving. So what I did here is I related my results to the literature. I made it fit in. How do these results relate to what we already know? I'm introducing some other information in here too, because where does it fit into the literature? So in some cases, you're going to talk about additional results different than what you found. And in some cases, you're going to say, how do my results mesh with theirs? Are they consistent? Are they inconsistent? Or how do they fit together to create some kind of unified picture? I'm not going to expect you to do all of this necessarily, but this is a very good goal to shoot for. You should definitely try to talk about each of these 6 things in all of your answers to the best that you are able. If you're interested in learning more about statistics, visit us at learnstats.com.